Welcome to Daily Papers.
If you've ever browsed a scientific journal online, you've probably seen them, those colorful, eye-catching diagrams right at the top of an article. They look a bit like a mini flowchart or a comic strip.
They're called graphical abstracts, and they're basically a movie poster for a research paper. Their job is to summarize the entire study in one quick visual snapshot to get you interested.
And they work. Papers with a good graphical abstract get more attention. But for scientists who are often more comfortable with words and numbers than with graphic design, making them can be a real headache.
So naturally, we're turning to AI. AI models are getting amazing at generating images from text. You can ask for a photorealistic astronaut riding a horse and get it. So why not ask for a diagram of my new protein folding algorithm?
Sounds simple, but there's a huge problem. And that problem is what today's paper, GenGA, Editable and Data-Grounded Graphical Abstract for Academic Papers, is all about solving.
The problem comes down to the difference between a baked cake and a box of cake mix. When most AI models generate an image, they give you the finished baked cake.
Right, you get a flat image, like a JPEG or a PNG file. In technical terms, this is called a raster graphic. It's essentially a grid of colored pixels. If you zoom in far enough, you just see little squares.
And what if you wanted to change something? Say your co-author looks at the diagram and says, "Can we make that arrow point the other way?" With a raster image, that's incredibly difficult. You can't just pick up the arrow. It's not an object, it's just a collection of pixels. You'd have to use a program like Photoshop to painstakingly erase the old arrow and draw a new one.
It's like trying to move a single chocolate chip in that baked cake. You can't, you'd just make a mess. This is a huge issue for scientists because research is all about revision. Figures go through dozens of drafts based on feedback from colleagues and reviewers.
So what we need isn't the baked cake. We need the box of cake mix with all the ingredients separate. That's what this paper's system called GenGA sets out to create. Instead of raster graphics, it produces vector graphics.
Vector graphics are totally different. They aren't made of pixels. They're made of objects, lines, circles, rectangles, and text boxes, all defined by math. Think of a PowerPoint slide. You can click on any shape, resize it, change its color, or move it around, and everything else stays perfectly intact.
This is exactly what a researcher needs. They need to be able to tweak and refine their graphical abstract easily. The GenGA system is designed to read a scientific paper and automatically generate one of these fully editable, vector-based diagrams. But the researchers didn't just build a new system, they realized they first had to define the problem in a new way. The goal isn't just to generate a figure, the goal is to generate an editable figure.
And to do that, you need a way to measure editability. How can you say for certain that one diagram is easier to edit than another?
They came up with a really clever metric called the Structural Independence Coefficient, or SIC for short.
That sounds complicated, but the idea is simple. Structural independence just means that the different parts of the diagram are independent of each other.
Think of it like a puppet. A puppet with tangled strings has a low SIC score. If you pull the string for the arm, the leg might kick out and the head might wobble. It's a mess. But a puppet with perfectly separated strings has a high SIC score. You can move the arm and only the arm moves.
It's the same with a diagram. A low SIC score means that changing one part might accidentally mess up another. Maybe a text box is fused to a background image, or two shapes are locked together. A high SIC score means every element is its own independent thing, ready to be moved or modified.
And they proved it. In a user study, they gave researchers different diagrams with different SIC scores and asked them to make edits. They found a direct correlation. The higher the SIC score, the faster and more successfully people could complete the editing tasks.
So, how does the GenGA system actually make these high SIC figures? It's a multi-step process. First, it doesn't start from a blank slate. It looks through a huge database of existing graphical abstracts from other papers to find one that has a similar topic or structure.
It uses that existing diagram as a kind of template, not for the content, but for the layout. It analyzes its structure, where the boxes are, how the arrows flow.
And then it reads the new paper it's been given. It understands the key concepts, the inputs, the methods, and the outputs. It also takes any specific images the scientist wants to include, like a data plot or a photo of their equipment.
And here's the clever bit. It populates the template with the new information, creating brand new text boxes, arrows, and placeholders for the scientist's images, all as separate vector elements. It's building the diagram piece by piece, like putting Lego bricks together.
But my favorite part is what happens next. It has a self-correction loop. Once GenGA creates a first draft, it hands it over to another AI, a reviewer AI.
This reviewer AI looks at the draft and gives feedback. It might say, this text is too long, or the flow of these arrows is confusing, or this part of the diagram doesn't seem to match the paper's main point.
The generator AI takes that feedback and tries again. It goes through this review and revision process a few times, getting better with each loop until it has a polished, coherent, and, most importantly, highly editable final product.
The results are pretty amazing. The graphical abstracts made by GenGA have significantly higher SIC scores, meaning they're much easier to edit than those from other AI methods. And user studies showed that scientists strongly preferred the figures made by GenGA, with 2/3 of them rating the outputs as good enough to be published.
What's so important about this work is that it's not just about creating a cool new AI tool. It's about building a tool that understands and fits into the messy, iterative reality of how science actually gets done.
Exactly. An AI that just gives you a final, unchangeable baked cake isn't a collaborator, it's a black box. By producing an editable vector graphic, the cake mix, GenGA acts as a true assistant. It does the heavy lifting of creating a first draft and then hands over an organized, flexible file that the scientist can easily refine.
It's a shift in thinking from just automating a task to actually empowering the user. And by creating the SIC metric, they've given the whole research community a way to measure how well future tools are achieving that goal.
It's a great paper that reminds us the best AI tools aren't always the ones that do everything for us, but the ones that work with us. That's all the time we have for today on Daily Papers.